Hello, hello. Yeah, what's up? Hi, welcome to 20B lecture from the remote parts of we're online today. We're not in person. So, yeah. A couple reminders before we start. So, you got your midterm, which I'm sure all of you know. Your midterm is next Friday. The 15th, unfortunately, at 7 p.m. As always, once we have a room, we'll announce it. Don't forget that Monday's a holiday, so you should enjoy your holiday, right? Don't come to class because once again, you will be sad, and I will be sad, right? So don't do that. That's bad. And since I'm not there as such, office hours will be canceled, and because I'm not back yet until Wednesday, the Tuesday office hour we need to reschedule because I have a meeting during that time. So, yeah, and normally this is the part where I would ask if there's any questions, but alas, this is a recording, so no such questions will be answered. Don't forget exam poker is still going, so yeah, try to weasel the hints out of me if possible. Okay, so starting today, we're going to talk about sequences. And so, see, I thought it wasn't as bad, and then I went over my notes, and, well, we'll see. Yeah, so now we're getting into the final part of the course, which has to do with infinite series, right? And this is notoriously hard, but it's okay, because we'll get through it. But, yeah. So, let's get into it, right? Let's get into it. So, a sequence is something of the form. So it might be like 1/1/2, 1/4, 1 to the 8th, right? So this follows a pattern. And maybe, I don't know, here's a sub n 0, 1, 2, 3, and then you realize that 1 over n, or here, let's use 1 over k actually. Let's erase that. Yeah, I'm on my friend's setup today, so this is actually nice. So you realize that, yeah. So sometimes it's nice and it follows a pattern, right? But it's some sequence of numbers, right? But maybe the numbers are random. Like they don't always follow a pattern. And this happens, right? Maybe it's like, I don't know, like 73 minus 1 over 2 million, right? And so on. And it's like, what's the pattern, right? Okay, so sequences could be anything, but all it really is just a really, really long list of numbers. So a sequence is an infinite list of numbers. Is an infinite list of numbers. Infinite ordered list of numbers. So here's the book definition, okay? The book definition likes book definition sequence. So they use this a sub n. And this is the notation for sequences, right? So this means sequence. This is the name of the sequence. And this one is the indexing variable. And that's typically how we'll do it, right? So all the pieces are there, right? Is an ordered collection of numbers. Yeah, and then the rest isn't important. We're not gonna worry so much about that. We're not gonna worry so much about that. Okay. So, yeah, it's one of those like, oh, should I be precise with definitions? Probably. Do I actually care? No, you can do that later. Yeah, I care more about you being able to work with this stuff. So yeah. So here we have two examples of sequences, and we're gonna do some a lot of examples of sequences. So the key important thing. So most sequences in this class do have a pattern. And so you should cultivate the skill of taking a sequence and extracting the pattern, right? So we're going to do a few together, he says as he talks to a literal camera and a screen. Yeah, we're going to do a couple together. So if you want, you can do the very strange thing of pausing the video and trying to identify the thing. Okay, but we'll do the first one together. Okay, so here's the sequence, right? 0, 1/2, 2/3, 3/4, 4/5, and so on. Okay, so here's the sequence. I want to be able to identify the pattern. Okay, so a sub n, this is called the nth term, right? And let's say we start at 0, right? So maybe this is, so I like to do this. A sub n, and here's n. So 0, 1, 2, 3, 4, and so on, okay? Cool. So, you look at this, right? How do I get a formula for a sub n? Well, you ask yourself, right? How do I take this number and make that one, right? So maybe your first guess is n, but that doesn't really make sense, because if you look at this second guess here, if I look at this one, how do I use the 1 to make the 1/2? Well, it looks like n over n plus 1, right? I take the number on the bottom and I put it on top, and I put 1 greater than that below it. Well, does that pattern work? Does that pattern work? Well, 2, let's put it on top and put 1 below it. Yeah, that works. What about 3? If I take 3 and I put it on the top and I add 1 and put it below, that still works. And it looks like that is indeed the pattern. That is indeed the pattern, right? Because, yeah, you just take the indexing variable, right? Here, check this out. A0 is 0 over 0 plus 1, which is 0. That checks out. A1, right, is 1 over 1 plus 1, which is 1 over 2, which checks out, right? Remember, we plug in this number into, oh, whoops, sorry. Let's, how do I undo this? Oh, there we go. Remember, we take this number and we plug it into there and plug it into there, right? So if you were to do that, let's try a couple more, right? A2 is equal to 2 over 2 plus 1, which is 2/3. So it looks like we found the pattern for this sequence. And this is a really important skill, because this is mostly what this is going to be like, okay? So let's do another one. Let's look at a sequence Bn, right? And I'll just write the n's below it. And you can do this however you like. 1, 0, minus 1, 0, 1, 0, minus 1, 0, and so on, right? So this might be hard, and there's a couple ways to do this, right? There's a couple ways to do this. So 2, 3, 4, 5, 6, 7, and so on, right? Okay, this one you can think about for a very long time. For a very, very long time, and you might not get it. And that's okay, because I'm just going to tell you what it is. If it's some kind of an alternating thing and there's zeros in there, maybe you try sine or cosine, right? So I'm going to try cosine, okay? So I'm going to put an n in there. And I'm also going to put a pi, right? And I'm also going to put over 2. Yeah. Oh, come on. I want just this one over here. Yeah. Nice. Okay. So let's try this. Does it work? Well, b0, right? You just plug in 0. Pi over 2 times 0. Well, that's cosine of 0, which is 1. That works. b1, what is that? Cosine of pi over 2 times 1, which is cosine of pi over 2, which is 0. And you can check that this works for the rest of them. Yep. And this works for the rest of them. Okay, there's one more important example I want to do, which is the following example. N. 1 minus 1, 1 minus 1. Here, we'll put commas. 1 minus 1. And so this is an, actually, let's make this a little more interesting. Let's make the numbers go up. So how about 1 minus 1/2, a third, minus a fourth, a fifth, minus 1/6, and so on, okay? So, ow, I just kicked the desk. That was painful. Here, I kind of want to start the sequence at 1, because it just looks more natural to do that, right? Now, there's a big debate in the world of mathematicians, which is some people start with a 1 and some people start with a 0. I don't care. It's just whatever makes your formulas cleaner, whatever you like, whatever helps you go to sleep at night, as long as you're clear about what the starting term is, okay? I prefer to start at 0 unless it's just much better to start at 1. In that case, then I'll start at 1. Yeah, I don't know. It's up to you though. Okay, so let's look at this. What does the pattern look like? It looks like this number always matches that number, right? It looks like the n always matches the denominator, so probably Cn is going to have a 1 over n in the denominator, right? But how do I account for the fact that it's constantly changing in sign? Well, if you don't know, it might be hard to guess, but we're going to put a minus 1 to the n here, okay? But what's the problem here? If I plug in C0, that's... Oh, wait, no, I can't plug in 0. That's bad. Let's plug in like 3 or something. What? No. Sorry. Technical difficulties. Okay. So let's plug in C1 is minus 1 to the 1 over 1 over 1, which is minus 1, right? But I'm supposed to get positive 1. And so that's bad, right? So this doesn't work. This doesn't work. But you can fix it by applying a slight little tweak. If I just added a plus 1 here, right? Now it works. So C1 is equal to minus 1 squared, 1 over 1, which is 1 indeed. And now this works. Check. So this is the formula that we want. So for, here's a pro tip, for sequences alternating in sign, use minus 1 to the n or minus 1 to the n plus 1 to alternate the sign. This is a good tip to have, right? And so yeah. Okay, so normally right here I would stop and take questions, but it's a recording and I'm talking to a camera, so we can't do that. Okay, yeah. So there's another really example of sequence that I want to talk about, which is the Fibonacci sequence. So we're going to define a sequence like so. We're going to start with 0 and 1, and each number is going to be the sum of the previous two. Right, so we get 1 here, then these two will sum up to this one, right? And then these two will sum up to this one, and then I'm running out of colors here. These two will sum up to this one, and then these two will sum up to this one, and these two will sum up to that one. Let's put some commas in there. And you get the point, right? 89, 144, and so on. So this is called the Fibonacci sequence, right? And it's very famous because it's in all these memes, and it shows up everywhere in nature, and like all these crazy facts about it, which are supposedly really interesting, right? But let's talk about it from a mathematical point of view. So I'm gonna write it like so. F0 is 0, F1 is 1, and I'm gonna write the following expression. Fn is equal to Fn minus 1 plus Fn minus 2 for n greater than or equal to 2. Okay, what does this mean? Let's write this in plain English. This means each term, right, and this says is the previous term plus the term before that. Right, if you just write it in plain English. Fn minus 2 is 2 terms before Fn. Fn minus 1 is the term before Fn, right? So if I say Fn is equal to Fn minus 1 plus Fn minus 2, what I'm really saying is that each term is the sum of the 2 terms before it. Yep. And so that's how you should read these, right? Each term is the sum of whatever expression on the left. So this type of expression, this type of sequence, we say is defined recursively, right? And all the CS people are like squirming in their chairs right now because they're very happy. But when we use previous terms to define terms that are coming up, we call that a recursively defined sequence, right? And these are very useful. These are very useful because sometimes getting a, here, I'll just write this down. Useful because some sequences are hard to find a formula for. That's such bad English. This is what happens when you live abroad. Your English deteriorates, right? But it is what it is. Yeah. So, for example, the formula for this, right? For example, okay, imagine trying to guess a formula for this sequence here. In fact, I want you to pause this video and just try to guess the formula. That's kind of brutal because it's pretty hard to guess because I'm going to tell you what it is, right? It's this. 1 over root 5. 1 plus root 5 over 2 to the n minus 1 minus root 5 over 2 to the n. That's the formula for what it is. Now, how many of you got it? How many of you got it just by guessing if you didn't already know it before? I would wager to bet that very few people would guess this out of thin air. So sometimes you want to use recursive sequences. Computers love recursive sequences, right? They just, it's great. Everything works out, right? So here's another example. Right, let's look at this one. So the compute A2, A3, A4 for the sequence defined by so let's say A1 is 1 and A2 or that was bad. Messed that up. I had one job. AN is equal to 1/2 AN minus 1 plus 2 over AN minus 1. So these are like these coming from these like weird continued fractions things. It's like actually really cool, right? But yeah, and we'll actually squeeze some of that in hopefully if we have time. But yeah, so you just do it. Whoops. So for n equals 2, right? What do you do? Well, so this is actually a really good thing. So plug the number you need. Plug the number you need to make this say what you want. So for example, right, sometimes this might say like n plus 1 or something. That's actually not a problem here. Here it's pretty easy, right? Here all you got to do is plug in n minus 2 or plug in n equal to 2. Right, that's all you got to do. So don't make things harder than it needs to be. So I replace every n I see with a 2, okay? 1/2 a 2 minus 1 plus 2 over a times 2 minus 1, right? And so now I clean this up slightly. This is 1/2 a1 plus 2 over a1, right? So that wasn't so bad. That wasn't so bad. And so now you just simplify that, right? Because we can plug in a1 like so. Right? You just do it. So this 1 plus 2 over 1, right? And so this is just equal to 3/2. Okay, so now we got a2. Now we got a2. So now we need a3, right? So and I'm just gonna do this super quick. 3, right? You just plug in 3's for all the n's. So a3 minus 1 plus 2 over a3 minus 1, right? And so that's 1/2 a2 plus 2 over a2, and then we plug in that which we had for a2, right? So remember, a2 was this, so we're going to plug that in, right? So 3/2 plus 2 over 3/2, and then you would solve that and get an answer, right? And so what's a4? I'm going to leave you to do a4. Why? Because I'm lazy. You should get 17 over 12, and if you did it right, you should get 577 over 408. Yeah, that's for you to do if you feel like it. If you feel like it. Okay, so now let's move on. Now let's talk about limits of sequences. Limits of sequences. And now imagine, this is the advantage of having recordings, right? I imagine someone's watching me on 2 times speed right now. And that's fine. That's fine. That's perfect. That's what technology is for, right? Where's that Diet Coke, Diet Pepsi? Ah, my sweet, sweet 0 sugar caffeine. But yeah, okay. So, sometimes sequences do this. This is approach a value. For example, if I looked at this one's boring, but 1/2, 1/3, 1/4, 1/5, and so on. If I draw a graph, right, like so. Oh wait, this is Notability. I think it does this, right? If you just hold it, yeah. Oh well, one of those lines is bad. Okay, but anyway. So let's say this is 1, right? And this is 1, 2, 3, 4, 5, 6, and so on, okay? And I'm gonna have these dots label the sequence. So 1 is at 1, 2 is at 1/2, 3 is at 1/3, and then like a 4th, a 5th, a 6th, and it just like kind of keeps going down, right? But it just keeps tending towards 0. So like, what does that mean? What does it mean that it's tending towards 0? What does it mean that it's approaching 0? Like, if I go far enough, maybe it hits 0 in some sense, right? Maybe you don't believe me here. Or like 1, 1/2, a 4th, an 1/8. Here's one with a formula, 1 over 2 to the n, right? And so on. Well, maybe that's approaching 0. And maybe it is, yeah? So like we want, and it is, that's why I'm telling you this, otherwise we wouldn't care, right? So we want some notion of being able to see what is so in some sense, the end of the sequence is interesting to us. And I love when mathematicians write this, right? Because they're like, oh, it's interesting to us. And I'm always like, well, is it really though? It's interesting to you, maybe. But so maybe this is interesting to me, but not to you. But let's just say it's interesting to us, as mathematicians usually do. Right. So let's come up with a definition, right? And so the end, or as with all things in life, the limit. Right? So we're going to talk about limits of sequences. Because, yeah. Limits of sequences. Okay. So we say, are you guys ready? That the sequence AN, right, converges to a limit L, and write AN. Oh, well, here. We'll do it like this. Let's do this. Move this here. We'll just do a new line. So there's two ways you'll see this written. Typically, you'll see that the limit n approaches infinity of AN is equal to L, or you might just write it like this. This is my preferred notation. I just think it's better, but you'll see the other one there all the time. If, all right, you guys ready? For every epsilon greater than 0, right, there exists, what letter do they use? M. M, such that, and we're writing it and we're color coding it for a reason. If n is greater than m, then an minus L is less than epsilon. Okay, I'm only gonna briefly go into what this means because it's not that important, but yeah. Yeah. So yeah, let's talk about what this means. So, whoops. I'm so used to OneNote. I forget Notability is actually good, right? I might not be able to go back after this. I might become stuck. Okay, so let's say here's your hypothetical limit L, okay? Let's say this is your hypothetical limit. This is hypothetical limit. So, and maybe your sequence looks something like this, right? Maybe it's like, and then after a while it starts to accumulate towards that limit. Maybe it looks something like this, okay? So you want to think of epsilon like a little slider, okay? Like maybe epsilon is like, so let's say here's 0, right? Let's say we choose this value for epsilon, right? So then I want to go this much above, right? Maybe like there. And that's L plus epsilon, and let's go that much below as well. Right? And that's L minus epsilon. Okay, all this stupid condition says is that there comes a point, and in fact it's right here, right? This is my M. There comes a point where the sequence is trapped between L minus epsilon and L plus epsilon. That's all it says, right? Do you see how when I chose that value of epsilon, there came a point I could cut the thing off somewhere at M right there. I could cut the thing off at M, and then the rest of the sequence is trapped between those two lines, okay? Now, if I can do this, for every epsilon. What does that mean? What does it mean if you can do this for every epsilon? Well, here, let's look. Yeah, nice. Okay, so if you can do this for every epsilon, let's say this is your hypothetical limit line here, right? And I get super close to it, like super close to it. Oh well, okay, maybe that's okay. Let's maybe let's go here. Okay, yeah, that's decent, right? Okay, yeah, whatever, that's close enough. Okay, so here's L plus epsilon, L minus epsilon. There's my L, right? And if you get super close to it and all the points are just kind of like trapped in the middle there, right? Whoops, that ignore that one. Yeah, imagine I'm like kind of trash compactoring around the line L, okay? Well, if you can squeeze around that line L, but I'm telling you, all the points of the sequence have to lie between L minus epsilon and L plus epsilon. In other words, they lie between those two lines. Well, doesn't that mean eventually the points all have to land on L in some sense, right? There's no more space for it. I squeezed it all out, right? Because eventually this happens. Like, eventually, right? Like, so if here's L, then, I wonder if it'll let me do it. It might just snap the line on top of it. Yeah, see, eventually that happens. And I draw L minus epsilon, that happens, right? They're so close together, I can't even tell them apart, right? But the points are still, but AN is trapped in here. After a certain point. So doesn't that mean that AN hit L in some sense, right? In fact, it does. So that's how we define the limit of a sequence. If that didn't make sense, just don't worry about it. Because I highly doubt we will make you do an n epsilon proof on the test, okay? So, and that might show up in the homework, and then you can come ask me about it during office hours, and then we'll make it work out. But I wouldn't sweat it if that's something that didn't make that much sense. Yeah, so, just, it's fine. Don't worry about it. It's fine. It's fine. So, if the limit does not exist, we say AN diverges. And, yeah. Okay, there's one other thing that's not that important. I'll skip. Okay, so yeah. So facts. If a limit exists, it is unique. Yeah. Because you can only approach one limit. Like, I can show that. But, yeah, just believe it. I guess fact. Because we'll save the facts for later. So, yeah, okay. So, here's an example, right? Let AN equal to n plus 4 over n plus 3. No, do I want to do it this way? Actually, let's cover the theorem before we come back to this. So, oops, yeah. How to compute the limit? Well, intuitively, right? It looks like we would kind of want to just do this, right? N plus 4 over n plus 3. Should these not equal? Should this not equal that, which is equal to 1, right? Well, okay, here, let's do some more work. So that's equal to the limit n goes to infinity. The proper way to do it would be to divide all the terms by n, right? Over n plus 3 over n. This is the proper way to do it. So we try to do this. We get 1 plus 4 over n over 1 plus 3 over n. These go to 0. And so you get 1 over 1, which is 1. Okay, so that's how we get the limit. You can do that. But the book makes a whole song and dance about the theorem. So I have to mention it. Theorem. Yeah. If the limit as x goes to infinity of f of x exists, and f of n equals an for all integers n greater than or equal, well, let's just say 0 or something. It could be 1. It doesn't matter. Then I'll have to say that an converges. Then an converges to a limit. And the limit as n goes to infinity of f of x. Sorry, x goes to infinity. Equals the limit as n goes to infinity of a sub n. Okay, in other words, just take the limit as n goes to infinity. Right? Just do this. This is fine. Don't sweat it. Yeah. Don't worry so much about it. I don't know why that they always like freak out and make you do that, right? You just do it's like, well, this is an important rule that we have to follow. And you can't break the rule, and I'm like, whatever. It's fine. It's fine. So here's an interesting problem. So an example, many of which we've done, let's compute this, right? N plus ln of n over n squared, right? So this is limit n goes to infinity of n over n squared plus ln of n over n squared, right? And so this first one is easy. It's just 1 over n, and we know where that goes. And if the limits were to exist, you should get something like this. So we're going to suppose they exist. Right. But then, oh, you know what? Maybe we don't have to split it up. But yeah. Here. Actually, I changed my mind. Let's do it the normal way. Boom. Okay, here. I haven't figured out how to use Notability yet, so it's okay. You get to watch me do it the stupid way. And some of you are probably writhing in your chairs like, no, just do it the easy way. I don't know how to do it the easy way. So you get infinity over infinity, right, in some sense. So this is an indeterminate form. And so we use the rule named after L'Hopital, but was discovered by Jacob Bernoulli. We use yeah, we'll just pretend n's a continuous variable. I don't care to all those mathematicians that are losing their mind right now, right? And so if I multiply through by n, right, well, you could just compute. This is 0, right? Because the bottom is infinite and the top goes to 0. So it's 0, right? Big bottom, small top, 0. It's great. So that's typically how you can expect the problems to look. And everything is great. Everything is great. So brief side note. And so this is why this is nice. Okay, this is why this is nice. Well, Yeah, so there's a whole family of sequences. We call these the geometric sequences. And they look like this. A sub n is equal to c times r to the n, right? So you got some constant, right? And then a number. Oh, here, let's use a different color. Then you got a number, right? And the important property is that n shows up only in the power, right? And if you have this key property where n shows up only in the power, we call that a geometric sequence. So an example, my favorite one that I spam literally every time I teach this class, right? Actually, the one we looked at, oh, well, here, let's look at this one. This is a geometric sequence because if you think about it, long and hard, right? Let's make a pattern. Let's find the pattern, right? So n. Okay, the numbers are going up by multiples of 2, right? So probably there's a 2 to the n in the denominator, right? Okay, but it's alternating in sign, so let's try sticking a minus 1 to the n there. That appears to work. Yeah, so this works. Okay, so minus 1 to the n, 1 over 2 to the n is minus 1/2 to the n. And so this is a geometric sequence. Yeah. And so we will just compute the limits. So limit n goes to infinity of c times r to the n is equal to, we'll just do it. So it's 0 if r is between 1 and minus 1, not including, right? It's c if r equals 1, right? Because it just is. And it's infinity otherwise. Or it's infinity if absolute value of r is greater than 1, and it's undefined if r is equal to minus 1. Because, okay. So I'll draw the last case. If r equals minus 1, you get minus 1 to the n times c, which looks like this. So let's say this is c, and this is minus c, and your sequence just looks like this. It just goes back and forth, right? And if it just goes back and forth, it never approaches a single value. And so, yeah, that's no limit. Never approaches a single value. And so that's why there's no limit. Okay. And so you should try to prove this yourself. Try to prove this. But if you don't, I don't care. You can just assume it, right? So for example, this goes to 0 because minus 1/2 is between minus 1 and 1. So examples of this, we'll just do this real quick. Minus 1/2 to the n goes to 0, right? 3 times, I don't know, what's the number? 1 over 29 to the n also goes to 0, right? But 1 over 1000 times 4 to the n goes to infinity. And the reason is because this has absolute value. Oh, here, absolute value of 4 is greater than 1, right? And so, yeah, I'll let you think about that one because it's pretty straightforward. So I think there's like 1 or 2 more things I want to get to, and then we'll be good. Yeah, okay. 1 or 2 more things I want to get to, and then we'll be good. So, okay. So I'm not going to write the limit laws, just hopefully you remember them. So let's move on to squeeze theorem, or no, let's organize it like this. So ways to compute in these limits, right? I guess more ways to compute limits. So one, the usual limit laws hold. And I'll just write the first one because the rest are literally the same. So assume all the limits exist. The limit n goes to infinity of like an plus bn is equal to limit n goes to infinity of an plus limit n goes to infinity of bn. And I'm going to put this in quotes because this is inaccurate. If you were to write that sentence, that implies it's always true, but it's only true if all the limits exist, which isn't always the case. But you can do stuff like split up the limit, you can multiply them, you can divide them, you can pull the constants out. It's just all the usual stuff that we do without saying. Also, the squeeze theorem is true. Okay, now some people call it a sandwich theorem. I think that's really lame and really stupid. Don't call it that. It's the squeeze theorem. You know, you want to squeeze it, right? I mean, like, you squeeze a sandwich, right? But you don't always sandwich a squeeze. Do you? I don't know. But anyway, so I'll write it if an, bn, cn are sequences such that let's see. Oh, okay. They want to be fine. We'll be precise. Such that for some m, if okay, here we'll forget about that bit. The point is that you want them to sandwich each other, right? So here's the squeeze, right? So here's the bread, and that's the filling. I guess if that's how you're thinking about it sandwich theorem wise. And I'll draw a picture so this makes sense. So here, let's get rid of this. Right, we gotta get rid of the evidence. And limit n goes to infinity of bn equals limit n goes to infinity of cn. Then let's say this is L. Then the limit of an also goes to L. Okay. Now actually let's put the then down here. Yeah. Now why is that? Well, let me draw you a really quick picture. That picture's worth 1,000 words, right? Something like that. And then all these math people get mad at me. They're like, no, this improper, it's imprecise, right? So let's say this one's an, and let's say this one's bn, and let's say this one's cn. Okay, so I know that bn, right? Let's say bn does something like this, and it's approaching a limit, right? And let's say cn does something like this. Yeah, but I know that an is trapped between them. An is trapped in between. So what happens? Well, it looks like if I have to stay between the green and the blue dots, I have no choice but to hit that same limit, right? I have no choice. Have no choice but to hit same limit. So let me show you how you can use these powers for good, okay? So how to use. Right, because that's what we care about, right? So, let's see. So what's a fun example? That was boring. Fine, we'll do it. Oh, you know what? This one's cool. This one's cool. This one's cool. So here's an example, right? an. Let's see. Is equal to minus 1 to the n. This trick works really well for alternating sequences, ln n, okay? And I want to show this goes to 0, right? But watch this. Watch this. So we know, right, minus 1 over ln n is always trapping minus 1 to the n over ln n, which is trapping 1 over ln n, right? Because it's either the one on the right or the one on the left, depending on the sign, right? It just depends on the sign. Minus 1 to the n is either going to spit out a positive or a negative number. But 1 over ln n goes to 0, and minus 1 over ln n also goes to 0. Therefore, minus 1 to the n over ln n also approaches 0. So that's how you use the squeeze theorem. Okay, I think that's a good place to stop. We've ran out of time. There's one more thing I want to cover, and then we'll dive into series next time. But yeah, enjoy your holiday. I hope this wasn't too much. And I'll see y'all on the other side.